Hi, folks. So just because it involves a little bit of additional theory and it helps to have a little bit of the math, I wanted to have a special video that is just focused on the application of Hamilton's rule to the parent-offspring conflict, which leads to the prediction of so-called dishonest begging. And sort of what even does that mean, dishonest begging? So let's take a quick look at this. This won't take very long, but the idea here is we're interested in the question of what is the parental investment that will be favored by natural selection, where you're considering a system where these offspring here all need to be fed by their parent. And so the parent can decide how much to feed these offspring, and the offspring can decide how much to beg. And that begging will be a cue or a signal, actually. The begging will be a signal to the parent as to whether the parent should continue to feed the offspring. And that sets up the potential for conflict about when and how often the offspring should beg. So let's just see how that all is going to work out here. And so the idea here, and we're thinking in terms of a so-called inclusive fitness, but the idea here is that there's going to be some benefit relative to fitness gain from feeding offspring. And it will diminish over time. And so the more parental investment, so the more milk provided by the parent to the offspring, initially that will increase the number of offspring will that will survive to reproduction themselves. But eventually, the more and more you provide, you don't get more and more offspring out. It kind of rounds off there. And moreover, the more and more you provide, the less and less you have available for future offspring. So this is the benefit for your current offspring. This is the cost, the number of offspring lost in terms of those future offspring. And so Hamilton's rule supposedly provides a way in which we can predict how much helping behavior, so how much feeding behavior, a parent should provide. And so Hamilton's rule is it has these B and C terms, the benefit and cost to the one that is providing the help as well as the one that is receiving the help. Now, when we're looking at graphs like these, where we actually have these fitness functions here, what is sometimes not as much appreciated is that in Hamilton's rule, the B and C that you see are actually the marginal benefit and the marginal cost. And so it is at any particular feeding level. So if I'm at this feeding level here, then this is saying that if I increase my feeding a little bit, then I will get a lot of an increase in fitness. And so it's how much extra fitness are you getting out of this new increment of help? So with a little bit of extra help, you get a lot of fitness out of it here. And so this slope on this blue curve, on this benefit curve, is very high. But at this fitness level, it's very shallow, it's very low. So this is saying that for the next increment of milk provided, the next increment of help provided, you don't actually get much more of a benefit out. You don't actually get a very much of an increase in this when you're at this level here. Now, down here, the cost, you actually have per every unit of milk you provide, you pay the same cost to additional future offspring you forego. So that's why this is a straight line here. This is cost. So this bends because you can't just, eventually your offspring fill up. And so, there's diminishing marginal returns in terms of your current offspring, but there is this linear cost in terms of your future offspring. So that's the idea here. Now, when we think about Hamilton's rule, it's saying here that the relatedness to the one who's receiving the benefit, that has to be greater than, so the relatedness to the one who's receiving the benefit times that marginal benefit has to be greater than the relatedness to the one who's paying the cost times that marginal cost is the basic sort of expansion of Hamilton's rule. So if you find that, so in this case, if these relatednesses are the same, then just for simplicity on this slide, then we can just say, is the marginal benefit greater than the marginal cost? And so over here, we see that the marginal benefit is much greater. This is a much steeper slope than this slope. So that would mean that you should invest more. So if you're providing this much milk, you should actually provide a little bit more than that. Now over here, this is actually shallower than this one here. So that means you're providing too much. So you're not getting enough marginal benefit out of it for the marginal cost you're paying. So you should provide less. And so the optimal investment is thus, and this is again, this is Hamilton's rule, just written in a way where we've split the relatednesses out. So normally you would see this as you divide both sides by one of these relatednesses. So you just get one RB is equal to C. But in this case, we've split them out. But this is just an equimarginal principle from economics. So it's just like supply and demand, and you get this equalization here. So this is basically saying that if these relatednesses are equal, then the optimal investment will be the investment where the slope at the blue line will be equal to the slope at the red line. That's all this is saying here. So let's break it out now and think about the parent and offspring together. Now, the parent sees half relatedness to um, both offspring being fed and offspring losing out. So the offspring that it's feeding right now, it's half related to because the genes came half from mom and half from dad. But that's also the case for all of the future offspring. So the future offspring that it hasn't had now, that the feeding that is going on now could help it produce later, those offspring it's also half related to. So you get the same relatedness on both sides here. So the one benefiting, you're half related to them. The one that is losing out, you're half related to them. So we would expect then that the optimal point for the parent will be where that FB curve's slope is going to be equal to the slope of the FC curve. So the marginal benefit will be equal to the marginal cost. Now, the conflict comes into play because this is not the case for the offspring being fed. The offspring currently being fed, well, they are 100% related to themselves. So that's very different there. They are half related to the offspring that will be generated later. And so there's a 1.0 relatedness to themselves and a half relatedness to the sibling losing out. So this is their optimal perspective, is that the marginal benefits to feeding, those equal out when they're half of the marginal costs to the sibling that is losing out to. So that's going to suggest there's going to be more feeding. So this is the way that looks here. So here's our fitness, the fitness being gained as we're trying to bring the current offspring to their own age of reproduction. And so that's this line right here. Here now are two different cost lines. This is the cost relative to the parent, because remember, the parent sees the same relatedness to both the current offspring and the future offspring. So it scales these two curves by the same amount. But the offspring sees 100% relatedness to itself and half relatedness to those future offspring that are losing out. So, in its perspective, it sees the same blue curve, but it sees a much shallower cost curve. So, if I look to see at what point on this bending curve here does the slope equal these two, I find that from the parent's perspective, then this is the optimal point. So the distance between these two lines is maximized in right here at this level of parental investment, this level of milk. And that will, so you can see this slope here on this line is equal to this slope down here on this line. But from the offspring's perspective, because this slope is so much shallower, then from that perspective, the parent should feed longer so that this benefit to the current offspring decays a lot farther until you finally get it to be shallow enough to reach this cost curve down here. So it's maximizing the distance between these two curves, which happens right here, whereas the parent is maximizing the distance between these two curves, which happens here. So this generates that parent-offspring genetic conflict. So we've got maximal inclusive fitness for the parent here, maximal inclusive fitness for the offspring here, which is suboptimal for the parent. And that is a key point here, that the optimal investment differs for these two different actors, the parent and the offspring. And that leads to this picture that came from the text that we use, which is the same thing that I just kind of drew out, but drawn out by a different author there. But the point here is that when you have this case, you then have to think, well, what is that going to do to the signaling that is being generated by the offspring? Well, what is a signal? A signal is only called a signal if it has a benefit to both the receiver of the signal and the sender of the signal. And so that's the whole idea, And so if you have something that is traditionally a signal that is evolved to be a signal, but then you also have this, which has occurred, then there is a temptation for the offspring to end up over signaling. And what do we mean by being dishonest over bagging or dishonest over signaling or dishonest signaling? It's the same thing as what we were talking about when we had fiddler crabs, where the fiddler crab with a really big claw, sometimes that claw is hollow. So it signals as if it is a big, dangerous claw, but it doesn't actually have any danger behind it. That would be a dishonest signal. And that only works if most of the fiddler crabs honestly signal. But then when that happens, then there's an opportunity every once in a while for a fiddler crab to make a fake claw, a cheap fake claw that looks like a big claw, and then it can survive, or then it can win that in that conflict there without ever actually having the claw that it needed if the conflict were actually to come to a fight. Well, there's a similar thing going on here, because what this is saying here is that um, the if the offspring continue to beg be for after this level of milk has been provided, at that point they are going to be, if they receive the milk, they will benefit themselves, but it will come at a cost to the parent. And so if the parent is responding to that signal, that parent is doing something which is not a benefit to the receiver. And so that ceases to be an honest signal. We would refer to that as a dishonest signal because it's benefiting one party, the sender, and is not benefiting the parent. So you would imagine that a parent might evolve ways in which it could detect when you've reached this point. Like, so there, if the parent and offspring are in agreement up until this point. And so the begging mechanism is happening, and if the parent responds to it, it's increasing the fitness of both the offspring and itself. But at this particular point, if the parent continues to respond, it's going to do a cost to itself. And so one would imagine that there could be an arms race that develops between the offspring and the parent, where the parent is going to try to detect whether the offspring actually has reached this point. And then the offspring is going to try to conceal how satiated it is, so that it can convince the parent to continue to feed it. And that's what we mean by dishonest over begging. So it's not that the offspring, it's not this. So there's a question that comes up is, well, isn't the offspring still hungry? And like, well, what does it mean to be hungry? So it is true the offspring could eat more. But the point here is, in terms of fitness, the signaling mechanism, signals evolve because they benefit two parties. And after this point, if the offspring continues to signal, then now we're in a point at which the communication between the offspring and the parent is in this manipulative area where it actually is going against the parent's best interests to give in to the offspring to benefit the offspring. And that's what we mean by being a dishonest overbegging. It's not that the offspring's asking for food that it doesn't need, it's asking for food that is going to take away from the parent's fitness in terms of future offspring in order to benefit the current offspring in a way that doesn't compensate for all of the losses it's getting in its future offspring. All right. I hope that makes it clear where all those things come from, and we will talk more about this in class.